Okay, welcome back to Feedback Control Systems. This is Module 9.2 titled Improving Transient Response via Cascade Compensation. The objectives of this module are to look at cascade derivative compensation, also referred to as PD or proportional derivative control. Then look at an example of the cascade derivative compensation. Then we'll look at an implementation of the proportional derivative controller. Then we'll switch into lead compensation, and finally we'll work a lead compensation example. So we're going to start with our cascade derivative compensation, or a PD control. You'll see the compensator shown here. It will be basically a 0, S plus ZC, where ZC is the compensator 0. And that's the derivative form. Now we're going to start by looking at an uncompensated system with the root locus as we show here. And what I want to do, just for a visual as we work through some of this, is actually draw the system representation. So we're going to start by looking at our reference signal, R of S here. Now that is going to be coming in with a plus. There's going to be a feedback term here with a minus. Now we are going to look at our compensator, so our GC of S term right here, that's our compensator. And then we can call it our plant transfer function, our G of S, it's right there. Okay, and then that's going to be fed back, and we're going to do a unity gain feedback system as shown here. So we're going to feedback with unity here, and then this will be our output, which traditionally we are calling C of S. So this will be our system. So we have our plant transfer function here, and here's our compensator that we're looking at for this. Now if we look at the root locus, we can see the open loop poles right here. We have them at -1, -2, -5, and then we're going to have a gain. So for this example, our G of S will just be our gain K, which we will vary via our root locus to find a suitable closed loop system. And then the poles are at S plus 1, S plus 2, and then S plus 5. Okay. So this would be our plant transfer function, and then initially what we're showing you on this graph, the uncompensated system, you can assume that this G sub C term right now is 1. It's basically not there, and I have this G of S. So we have our open loop poles, and as we change our gain, we could get our closed loop characteristic. So how we get our closed loop characteristic, that would be our T of S. Okay. And what I will do is write that down. So basically we'd have this term over 1 plus this term. And then once we do some algebra to get it out, I'll write it in its final form right here, where we have our K in the numerator. And then it's going to be an S cubed plus 8S squared. And then plus 17S. And then plus 10 plus K. Okay, so this would be our closed loop system. Okay, one thing we can immediately know here is with the final value theorem, we can kind of already predict where we set our S is equal to 0 here, and what we'll see is this term right here, K over 10 plus K. Depending on the value of K, we're going to get a steady state error. For example, if we did a step input here, we're going to get a steady state error just based on this closed loop transfer function. So I just wanted to set this up. Here's our uncompensated system here. Now, depending on the value of K we desire here, if we wanted a certain damping, in this case 0.4, what we did is we swept and we got a value of K here of 23.72, and then we could basically factor, find the roots here in the denominator of the closed loop transfer function for that value of K, and then what we'll find are we have these dominant poles here, the closed loop poles. You're going to see a third pole right here just to the left of -6, and then the two poles right here at minus 0.939 plus or minus J 2.151 for that value of K. All right, so that's our uncompensated system. Now what we can do is look at a few different compensator designs for our GC of S, and then you can see our GC of S term right here. So we'll look at different compensator zeros here. So the first one, we're going to put a compensator 0 at -2. Now, why would we do that? You can see that right there. Well, that compensator 0, essentially, at -2, that's kind of going after this pole, right? And see if we could have essentially a pole 0 cancellation. So also, if we wanted to maintain that damping, you can see a increased value of K from 23.7 to roughly 51.25. We achieved the same damping. We're still on that 0.4 damping line, but notice that the poles will move accordingly from that cancellation with the pole at S-2. Then we can look at a compensator if we move the 0 to -3 as shown here. We can also, again, vary K to get on the same damping line as shown there. K would come down kind of between those two cases. And then finally, what if we move the compensator 0 at -4? Again, on the same damping line, K would come down even below our original uncompensated system. So the reason for this is I have a table here where we can kind of compare. And as we do some design, that might be what we're trying to say when we're designing this compensator here. We have some flexibility. We can choose essentially where we're going to put that compensator 0. And so you can see the different systems here. So you could look at different figures of merit. Well, we already know the percent overshoot here is the same for all because we're on that same damping line. So that's essentially a wash. But what we can see is we can have impact on our settling time and our peak time. So with the compensated systems, you'll see the settling time is faster. So that might be desired for your application. So again, you can kind of go through and simulate that. And then also what we see for all of this in the comments down at the bottom is that we can achieve a good second order approximations because of either a cancellation of a pole or where the dominant poles are. So here, finally, what you'll see are the various plots showing, again, the faster settling time for all of the compensated systems, and they all kind of have about the same overshoot, which we would expect based on the damping, etc., and overall less steady state error versus the uncompensated system. But just as we predicted here in the pink, we do have steady state error relative to this design. Okay? So that's kind of an overview starting point. Now I want to work an example here. So we have a different G of S here. So this, again, was for the last slide. I'm just going to leave this up here for now. We see on this slide now a new value of G of S that's given on the slide. So our first thing we want to do is look at an uncompensated root locus based on this system. And if we desire, let's say, a 16% overshoot, that would lead us to a damping line of 0.504, and that's what we see right there. So let's just say that's our desired overshoot, our max overshoot that we can get. Just immediately draw that line at 0.5, and that'll be our damping line. And then we can look at our open loop poles right here. We have a pole at S0, S -4, and then S at -6. These are our open loop zeros. And then as we vary K, the 0 and the 4 poles will come together and then essentially go off axis. And what we want to do is have it meet on that damping line of 0.504. What we'll see to get that is we get a K of about 43.35. So from that point, what we can do is with the values of the pole locations, what we can do is find omega n. And so what I want to do is just draw a quick reminder in the complex plane. For a pole location, for example, if that's our pole location, we know where these real and imaginary parts are. So the real part, what we had said is, we can call that sigma, and that is going to be negative the damping times the natural frequency. So that's that location. And this on the j omega axis right here, we call, for example, we know this is our j-axis. We can call that omega d, the damped frequency, which is also going to be equal to the natural frequency times the square root of 1 minus zeta squared. So given this information, we know where our pole is. We can go back. We see it relative to here. We see that, and what we can do is find the natural frequency. So what we found previously, we'll switch colors here. What we found is this length. This length is omega n, and this factor right here, we said we can call that value theta, and then the cosine of this angle was indeed the damping factor of zeta that we saw here. So I'll just write that down real quick. Cosine of that angle is basically our damping. So we can find omega n, shown here, just with the Pythagorean theorem. We know this base, we know this height, square root of the sum of the squares would give us omega n. That's what I'm doing here on the graph to find our omega n. Now, for finding omega n, what I am doing is, let's stop and let's go back to our goal for a second. We want to design a proportional derivative compensator with a 16% overshoot and a 3x reduction in the settling time. Okay? So what I'm trying to do is, from this uncompensated system, say, hey, what is the settling time? This was an expression we found in modules 4.1, 2, 3, 4, etc., in modules, that section. And so if we know omega n in zeta, we can find the settling time. And so what we found for this uncompensated case is roughly 3.32 seconds. Okay? And we found that at a value of k shown right there. And so when we looked at this root locus, we have these dominant poles, but we also have a third pole over here at minus 7.6 roughly. Since that's roughly 6x farther away from the dominant poles, our second order approximations are valid, and therefore we can use this equation for the settling time. Because again, please remember, those equations developed were for a general second order system. Here, if we have a third order system, we have to see if we can actually use those or not to give us good or accurate results. In this case, we're okay. Now, I'm showing this table here mainly for the uncompensated system, this column right here. Eventually, we'll get to the compensated system here. I just wanted to kind of put that table up, and as we go through, we can eventually do some comparisons, but I'll save that for a little bit later. Now, looking at our compensated design pole location, we want this to be 3x reduction in TS. So here our settling time was 3.32, and what you'll see here is our settling time is roughly a factor of 3 lower. So that would give us our sigma here, our sigma on the real axis. That comes out to be 3.613. And then we can find, so that's our sigma, and then I can also find my omega sub d on the imaginary axis as shown here with a little bit of geometry. So I basically now have my sigma, my omega d. I can actually now plot that and see that, but I also want to remain with that overshoot, so I'm on the same line. Notice originally here I had my dominant poles at minus 1.2 plus j 0.06, but now here I am, I have those poles migrating up that line, same damping line, same overshoot, but I'm migrating up, and so that will basically be our desired compensator pole location, okay? And you can see the uncompensated system down below just for reference, okay? Now what I'm going to do is I took that plot on the previous slide, brought it up here again, and now what I want to do is, based on that pole location for the compensated pole, if I were to do the sum of the angles based on there, I'm going to get a total value of minus 275.6. Well, what I need to do is I need to find the contribution of a compensator 0 to actually get me on that point, because I need what? I need those angles to sum up to an odd integer multiple of 180 degrees. So I'm at 275.6, subtract that 180 from that, and I'm left with the angle of 95.6. So I can now put my compensator 0 at this location. It looks close to minus 3. We'll solve for that. But notice that angle there is 95.6 relative to that compensator pole, so that we get that 180 degrees total value. And then, therefore, that pole will actually be where I want it to be. So to solve for that sigma for that 0 location, again, I will use geometry. I'm using the values here, 6.193 and 3.16 from the compensator pole, and then I figure out where my sigma needs to be for my 0, solve that with geometry, and I get a sigma of essentially 3. And you can see that on the pole 0 plot right here, that my compensator 0 is, for all intents and purposes, at -3. So now I can look at the root locus for my compensated system. So I have my compensator 0, and with my compensated system where the dominant poles are located, and so this would actually be sort of what the root locus looks like. So again, what happens is this pole at 0 originally goes to the left, so all poles trend to zeros, whether they're finite or infinite. In this case, I have a finite 0, so that pole is migrating to the left. Now these two poles, as I increase my gain, come together, go off axis, and then they have to go off to these zeros at infinity. So you'll see there's 0 here and then down here as well. And so that root locus will actually go through that compensated pole, because why? We know the angles. Once we included that compensator 0 now equals a integer multiple of 180 degrees. And again, I can find the value of k for that. In this case, it's 47.75. Then what I could do is I could go back to the table, we'll do that in a second, and compare through simulation a step response. So the black waveform is the uncompensated system without the controller, and then the compensated system, one quick comparison you'll note is they have about the same steady state error. The compensated system is quicker, faster settling time. They have about the same overshoot. Why? Because we designed it on that same overshoot damping line. And so, again, you could kind of go back and forth, and I'll do that looking at this table. So let's actually clear all the ink, and we can actually now compare the uncompensated and compensated system here. And actually look at some figures of merit. So again, the percent overshoot, again, if we did that comparison, is the same. Now, I have these other columns here through simulation. So that's important because as we do our calculations, looking at this system, it's what? It's a third order system. So when we did these approximations of a second order system, again, want to stress to you that these are only approximations and that you really need to use simulation to verify your calculations here. So again, these are all calculations, and the simulated values are shown here. So you'll see the percent overshoot. We had predicted 16, you're getting 14.8, probably close enough. But if not, you may need to tweak the design a little. Okay, and then what we can see is in terms of our settling time, we saw for the uncompensated system about 3.3, and then for the compensated about 1.1, which was again what we wanted, that factor of 3 reduction, right? A 3x reduction in the settling time with the same overshoot. So overall, I think, relative to our goal, we can feel pretty good relative to that in designing our proportional derivative compensator. Now, in terms of implementation of that compensator, and again, I know this wasn't the right problem, but here's our compensator. In terms of implementing it, as we see here, for a proportional derivative controller, we saw this in a previous module for the PI controller, but now this is set up for a PD controller, and then so we can literally go through this design process and then take our system and come up with our gains of K1 and K2. And so I just wanted to kind of put that out there, and we'll talk a little bit more about that as we go forward. Now I want to switch into lead compensation. Before we talked about PI and lag compensation. This module we're talking about PD controllers and lead compensation. So the approach here is, again, as we are looking at our pole 0 map, the sum of the angles from the uncompensated poles and zeros and the compensator pole and 0, to have this point be a desired pole location on the root locus, right, we need this integer integer multiple of 180 degrees. So you can see, based on maybe I have 2 pole locations, P1 and 2, which are my uncompensated poles. I have my uncompensated 0, and then here are my compensated pole and zeros that I have there, and you can see all the angles that we have here. And so what I'm showing is that the compensator angle here between the pole and 0, theta sub c right here, I can define my compensator 0. When I look at this, however, there are really a quote-unquote infinite number of possible compensators in terms of the pole and 0, right? I could have the pole here, the 0 here, then I could move it, but they're going to have to kind of move such that those angles always equal, again, that odd multiple of 180. So typically what you'll do is you'll pick one and then solve for the other. And then so you'll see that in some of the examples. In this case, here's the example where I want to walk through it. So what is our goal for this example? We want to design a lead compensator, 30% overshoot, and a 2x reduction in the settling time. So here's our open loop system. And what you'll see again here in black is our open loop poles. So we know we have them at 0, -4, and -6. There are our open loop poles that we have there. There are no zeros. Why? I just have a K in the numerator. There are no open loop zeros in this case. So if I know I want a 30% overshoot, that immediately says I can draw my damping line at 0.358 and then look for the desired poles in my system. So relative to our uncompensated settling time, what I could do is use this formula as shown below, sweep essentially a value and try to find that settling time given the damping, which I know, and the natural frequency that I know. And so for this case, for a gain of 63.2, this root locus would, I'm not showing you the root locus, but the 0 and the -4 would come together, go off axis. The -6 goes off to infinity to the left. And then so those come together. And then with that root locus, I would end up with a gain of k at that point right there. And then given those locations, again, given these locations for sigma and omega d that I have here, I could find omega n, and then I know zeta, so I could find my original settling time just under 4 seconds. Now, if I want that a factor of 2 lower, I'm going to be just under 2 seconds. Okay, so that's the approach, how we found the uncompensated settling time. And again, now we have our goal for our compensated system. So with the compensated system, similar to what we did with the PD approach, what we want to do is, since we know our new settling time, I can create my new sigma, same damping line, but I'll create my new sigma based on this reduction. And again, sorry about that. That was a error on my part. That should be 2x reduction because we said 2x. Now the number I believe is correct right there. Okay, so that's just an error. Sorry about that. 2x. Now we can find our sigma and our omega d. So our sigma and our omega d such that we are on that damping line with our new desired pole location. And then so you can see the values here and how they get mapped into our desired location right there. Very similar approach that we took from the previous PD example. Okay, so now as we're designing this lead compensator, remember we have an infinite number of choices of pole zero, so we said typically you pick one. And so I decided to pick a compensator 0 at -5, and then you'll see that on the next slide I have other options summarized. And again, this is part of the design art that you will learn as you go through some problems here. So assuming that compensator 0 here at -5, not shown on this root locus, but you'll see it coming up. We're going to do the sum of the uncompensated poles and zeros and that compensator 0. We'll see that that angle comes out to be -17.7. So that means our compensator pole would need to contribute about 7.3 degrees. So given that, notice that's positive, so that will have to go here to get a positive 7.3. And then I know my dominant poles and zeros right here. And so that's what we see here and here. So that's where that's located. So relative to that, I need that compensator pole to the left of that real axis component of the dominant pole. I need it here to get a positive angle, right? Okay, and again, clearly this is not drawn the scale because that's only 7 degrees. So again, just wanted to make note of that. So from that, we can solve from the geometry and find where the compensator pole would have to be. And it's all the way out to roughly minus 43. So it's kind of way out there. And so what you'll see is for the 0 at minus 5, okay, here's the 0 at minus 5, and then the pole, compensator pole at minus 42.96. Now what's going to happen with this root locus, we have our sort of our comparison. So here's this one, the case A for that case s plus 5. Here's one where we put the 0 at 4, and then here's one where we have the 0 at 2. Okay, so you can actually see the second case would be essentially a pole 0 cancellation there, and then the other case would be here. So we're only showing you the root locus for that one case, but here I'm showing you 2 other cases. And then sort of the summary sort of graphically here due to a step response, what you'll see is relative first to the uncompensated system here in black, it's the slowest of the cases that we looked at. The compensated cases have a faster settling time, and remember our goal was a factor of 2. So again, that's what's highlighted here, is we have originally sort of 4 going to 2 seconds approximately, so that part of the goal was achieved. The percent overshoot for all of the cases was designed to be 30, but notice here, I want to draw your note to this note down below in the table. The simulation results are actually shown in the parentheses. This is very important. When we have, again, our 3 poles, a third order system, and we are making approximations here, notice the following. The percent overshoot in all the cases was 30. That was the desired. But in the parentheses here, these are the simulation results. And so what you'll see for compensator C is that the percent overshoot for compensator C here in blue, right there, okay, it's about half. It's about 15 as opposed to 30%. So again, you can really, maybe you could say you exceeded your goal by making the overshoot come in lower. So that's something you can look at as you're designing these compensators. Okay, but in all cases, the settling time, which was the primary goal, was cut in half. So you could look at all these other characteristics here in terms of comparing the different compensators. And again, I think once you do that, you should hopefully make some determinations for yourself. Okay, so that concludes this module where we introduced the concepts of PD and lead compensation in our systems, and we walked you through some examples. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.